Over in Australia and North Queensland, we're seeing private LTE solutions being rolled out in the mining industry at a rapid rate. It's a new technology. It's the buzzword along with 5G. But now that they are getting to a stage where they've deployed the solution, they're looking at the fact of what's actually being delivered across the solution. And everyone that's been involved in mining knows they don't actually do, throughput capacity testing. They just see a technology, load it up until they reach capacity. Exactly. And with LTE, they're thinking they're getting an iPhone. They're thinking the data throughput they're going to get is an iPhone. And the reality is they're not getting anywhere near that. They're not getting anywhere close.
So what you're saying is there might be an initial lack of capacity planning, or they might not know the application.
From my point of view, it's a capacity planning issue, but it's just an understanding of the technology. They've been sold a technology by a very good salesman without the understanding about how the technology works. LTE is all about downloading information, not about uploading. And we are in a business of uploading data to a centralized point to gather that information and to utilize it as it's needed. So just off the basis of that, it's reversed in the way it needs to be utilized.
So an LTE salesman not understanding the application, not being able to do application planning.
Yes.
Capacity planning.
Capacity planning.
Yeah. And we've seen that like just recently this year. I was assisting one of the LTE mine sites with their autonomous truck. Now, every time that truck ran, it was generating a log file of 12 gigabytes of data per run. And they would do 10 to 12 runs per day. That LTE system couldn't upload, like you were saying. It couldn't uplink, right? So they had to stop the truck after each run and go and plug in a laptop with an SSD drive to do the download after each run. And that's just one of the shortfalls that we actually see.
Indicating the whole reason for the network in the first place.
Absolutely.
Yeah, it's time and time again we're seeing these new deployments go in. They want to run CCTV over it. Well, that's great, but you don't have the uplink capacity. And a lot of it's around the technology, not the overarching coverage that LTE provides, not the other than the capacity that the tower or the Bs that they're utilizing can handle. It's all about how much data they're doing off of that platform and what they're trying to push into the air. And when you've only got one transmit antenna, because the user equipment, the UE, whatever they've defined it as, that is going on a truck, an autonomous system, a heavy dozer, a loader, grader, a drag line, it's got one transmit antenna. It can only achieve through physics, 10, 12 megabits per second in a vacuum.
Yep.
And being a private spectrum, you don't have 20 megahertz of contiguous channel allocation like the telcos do. Yeah. You get 5, you get 10. And even if you are lucky to get 20, you're still restricted by the end user device, which only has one transmit antenna. And, the salesman will spin you that it's got 2 transmit antennas and it's using, transmit diversity. Well, transmit diversity is still one transmit antenna.
Yeah.
I think one of the biggest difficulties when you're trying to, even if you're competing against LTE, is how they can't demonstrate it until it's in. That's one of the biggest problems. Is LTE networks do take time to settle. It takes time to gather that coverage, just like and 5G networks as well. And so
to finally optimize.
Not only to optimize, but the whole system to settle down. You set up a mesh link, you know what your RSSI is, you know what the RSL is, you know those parameters, and you can tune it and fix it during the installation. What I've seen from port installations and their complexity and how they change is how LTE fails to adapt, I suppose, but also takes time to settle down into a state in which it's functional. And to demonstrate that technology, to demonstrate our technology as well, it's to do it on scale. But what I do know is that when you install more mesh nodes, you're strengthening your network by offering different routes for the data to travel, more redundancy, more capacity, and certainly with the processing power that we have now in some of the modern units. With LTE, you're always going to suffer with the same drawback, which is you include a subscriber, you are hindering your network. Like any TDD technology, you are drawing away from a central capacity. We're sharing attention all the time. We're not strengthening it. And so scalability is the big thing, I think, with ports anyway. But they're obviously very challenging environments. And there are some things which LTE does well within them. And when the infrastructure exists, there, but in general, the scalability and the settling of that infrastructure is what I think they find challenging.
The scalability is an interesting topic. So if we look at most of the regions that has high population density, where spectrum is scarce, so that's what we're experiencing in Asia Pacific, that's what we're experiencing in big parts of Europe, you do get, if we refer to Scandinavia, low population density where spectrum is not an issue anymore. So what is interesting about that is now even if we get spectrum potentially, we still have similar experiences with 4G LTE deployments. So we've seen this in ports, we've seen this in mines in Scandinavia.
Which is true that in both applications, when customers bring more and more advanced technology in their operations, like teleremote applications, autonomous applications, the uplink need is so high that any cellular application cannot support that. Yep. So that's the general problem in cellular technologies at the moment. So capacity problem.
Ports and mining, both.
Do you have, out of interest, you know, what I see, because I mostly did in maritime, so offshore, and ports are more of something I'm trying to move into. So it's a sector that's very interesting. We've done a few, but most of my customers are offshore, and so even if they do have port infrastructure or some buildings, if you look at Southampton, for example, that's owned by ABP, and then it's, you know, several different companies working within that. They want connectivity out to their fleet, and they want that to be on the same network as what's in their ports. And that's when I'm getting an issue again of losing range out to sea, and something which is impossible to test. They say, you know, I always get the question, can we do a demonstration side by side? We'll put one vessel out there. Well, that's not good for testing mesh at all, because it's one vessel. And it's not good to testing LTE either, because it's one vessel. I do, however, know which one is going to cope better when you, again, scale up and you have a fleet of 20 vessels or 50 vessels, or how many vessels it is. With projects at the moment with land reclamation, for example, where it's ever changing, you know, and you can build that infrastructure up.
Yes.
We're not being able to prove competitively in a sensible way how scalable things are, because you can't put all the infrastructure out there for free. It would be a completely ludicrous business model. So it's tough, but I don't know if your customers' imports are then expanding out to offshore as well.
What we have seen, and this goes back all the way to the industrial equipment manufacturers, and this is both ports and mining. What we've seen is on that level, with the original testing, maybe testing of communication solutions, back at that source, they don't even scale. So we've seen this so many times that this works across this technology, maybe a 4G, 5G. Let's simulate, we're testing a single machine. Let's do 2 machines. Let's do 3 machines. It seems to be working. Now let's deploy it. But in the real world, we are doing what? 10, 15, 20, 30, 40 machines, potentially, and ports sometimes up to 150, 200 machines. So we do find that scalability is mostly not being tested.
And all of those environments, mining, ports, maritime industry, constantly changing. So
yes, constant change.
Huge problem.
Another thing on ports is, sorry, not to only talk about ports, but they have fiber installed. They have fiber rings installed, right? Yeah. That's what ports have.
It's a good environment, yes.
You have a fiber ring. They are just in there.
Yeah.
Well, LTE isn't really going to benefit from that existing infrastructure at all. You know, it's on you know, it could be private, I suppose, but the systems which my career was based on benefit from that existing material, which has cost a lot of money to put in place.
Yeah, the shared model won't benefit from that. But if we focus on private, which is something we find often in Scandinavia and some other places in Europe, we do find that private, yes. What's interesting about private then is they require fiber. So we have an issue where with mines, maybe large surface mines, now they insist on having fiber. Synchronization of base stations is important. You cannot do that just over any link. You have to have fiber or fiber-like connecting up. So it's an interesting. There's a pro and a con there, but on both sides. How about coverage? General experience and coverage, because I know we have a consistent issue, ports as well as mining, a coverage issue. and the difficulty in expanding that.
That's one of the other big things that they get sold. Sorry, they look at their phone, they know they can get coverage pretty much anywhere. So they assume we're going to put 3 beads, we're going to put some sector antennas on a tower, and the mine is going to get covered. Well, the reality is, propagation works the way it works. It's affected the same way as all other RF is affected.
And mines change.
And mines change. 90-degree mountains appear out of nowhere almost overnight. Where they don't have facility, and it's not a cost-effective functionality to start having ENO-Bs on multiple trailers and moving them around like you would.
It's not an easy process.
No.
Well, one thing that I was amazed at when I first came across the ENO-Bs was high power device meant to cover a very, very long range with directional antenna. And that thing was actually depressed to go into the mining area itself, right? So the whole range benefit was lost because we were actually now depressed into the working area of the mine.
Yeah. Physics.
Then that was, that threw me a little bit, right? Because I was expecting to get 14-kilometer range, but we couldn't, because the mine was only 5 kilometers long, and the whole thing was depressed all the way down. So now the focused RF is actually going into the pit. We've lost that long range capacity that we were told we were going to get.
So this brings up an interesting angle where if you contrast where kinetic mesh came from, it was developed from an industrial perspective. If you look at where cellular 4G, 5G was developed from, it was from a broadband, consumer-based broadband perspective, where coverage is measured in horizontal range.
Yes.
Yep. Where we come from, coverage is measured in some horizontal, but a large amount of vertical coverage.
Yep, absolutely.
So once you get terrain deviation, this becomes a major issue.
The basic mining environment, in surface mining environment, the bit goes deeper all the time.
Yes.
But on the other hand, the waste rock dump, it's growing. That's the big problem, because you need to be constantly changing the base station radios direction and adjusting those
changes,
which is very expensive in overall.
And that's exactly right. All intensive purposes, a new solution rolls in, radiant kinetic mesh, LTE, whatever it's going to be, you'll have a 5-year mine plan. You'll have an indication of where your infrastructure needs to go. But I can tell you now, having gone through this myself, that mine plan is only as good as the day it was written.
Correct.
3 weeks later, you can be sat there getting ready to install your tower to find out they've mined out that area because there was a new seam that they identified, and it was cost effective, easier to adapt to, and to just get the asset out of the ground. And now I no longer have an area that was a key focus point for the network to radiate from. So now we've got to go back to planning again. And LTE doesn't have that flexibility. It's not designed to have that flexibility. Telcos don't use it in that manner.
No.
They use it on buildings and houses and on farms to get the coverage they need over a large mass area where they expect nothing to be in the way or for the terrain to change.
Where the terrain does not change. So this is an interesting similarity between ports and mining, where your customers build obstructions to your network on purpose.
Yeah, that's right. Yeah.
Which is the essence of their operations.
Customers will call us when they, in this case, they don't fully trust what they have installed, because it's based on coverage, right? If a node B fails, that node is gone, or that close to the crusher is gone, the coverage, right? So they call us and say, hey, we need something that can be worked together, because we have spent millions of dollars on this and we can just not throw it away, right? So we come in, we have this node called Peregrine LTE. It seamlessly integrates with the core LTE. Basically what we have to do, we install a slipstream, plug it to the core network. It's going to have a route through it, right? And then you plug the SIM card into the LTE node. It becomes a client. You plug whatever you need to plug behind that node, put in a truck, in a shove, or whatever. And then that node is going to now talk through mesh and through LTE simultaneously. One route is always the chosen one. So the other one is going to become like a backhaul, but it's already known. So let's say the mesh is pushing 20 megabits, and now that machine has moved, and then it now just needs 5 megabits. and LTE is better in that region, that's boom, gone. So mesh is going to be weaker in that region, and LTE is going to be better, for example. Or the node is needing 30 megabits. LTE in that area is gone. No 30 megabits.
So to summarize, how does the customers find this hybrid solution?
They find it very suitable. I mean, it's easy to install. It's just a regular node. You plug in the SIM card and gone. That's it. It's really good.
Problem solved.
Problem solved. And it is scalable.
Scalable.
Really scalable.
Scalable.
And the mesh network is based on offload, right? So we are not coverage based. So as soon as we start putting APT through fiber or through a PTP link, that area is covered.
Yes.
Right. So you create a small node, a small area. This node on a drill is pushing 15 megs. LTE will not do that on certain bands. So that drill is pushing 15. That node is capable. That link is capable of 100 megs, and you are good to go. Right. Now you need a new drill on that area. The area is going to talk to the node, and that 100 megabits link is good too. Right. And that area is served by mesh through the PTP link back to the APT that is the master, right?
For me, this is the future.
Yeah,
this is the future of
integration
and private
and it's
LTE solutions.
It's layer 2 integration.
Yeah.
There is no layer 3. It talks all the layers, but it's pretty easy to install.
How do you just sort of? I'm sorry.
Yeah, go for it.
How do you address concerns of customers that are particularly concerned with security? I'm talking about network security, encryption levels, things like that. With having a mesh solution, which I know is extremely well encrypted, something which goes outside and pulls outside of it.
Sure. The mesh itself, we work with this concept of encapsulation, de-encapsulation. Mm-hmm. It's done by the node that we call master, right? So with the slaves. So there is, the network is not. So if you go there with your cell phone, you don't see Rajant because it's not there, right? It's working, but your cell phone you won't pick it up, right? You can publish some SSIDs if you want, right, to serve cell phones, applications like this. But beyond that, you have the nodes. They are capable of high level of security. You just enable it's hop encryptation, MAC encryptation. It just works. Right? And it's pretty easy. Once you do in one node, you have to apply to all nodes because it's going to get encrypted on the way in. It's going to traverse the mesh. On the last node close to a drill, it's going to decrypt and deliver the information to the drill and vice versa.
So end-to-end encryption.
Yeah, end-to-end encryption. If you sniff with a Wireshark, you're going to see nothing.
Does that extend to LTE links as well?
Yeah, because the LTE we call RPT, remote protocol tunneling. It's encrypted end-to-end layer 2 connection, so it's very fast.
So one of the big things that I actually found during testing on a mine site, and it was good because the client was actually sitting next to me watching it happen.
Yeah.
I didn't realize that the day that I was actually doing the integration testing, they were going to be doing some power routing to the LTE tower because they wasn't connected to permanent power. Unbeknownst to me, they cut power to the entire tower. But I'd actually set up nodes to plug in via our normal mesh connections like APT nodes and all that sort of stuff. So I watched my LTE connection that I had during the testing just disappear. And I thought it was the first nodes that we'd ever released in the world. So I thought I made a mistake and I've damaged something, right?
Yeah.
So I mucked around for about a good 2 hours. And then afterwards I was like, no, hang on. And I went and asked someone and said, what's going on? They said, oh, sorry, we forgot to tell you. We've cut power to what's named to this tower. I was like, now you tell me. And they said, yeah, but you've still been able to hit all the switch infrastructure and you've still got video coming in and all that sort of stuff. And I said, yes, because I have redundancy. And that's when they clicked and went, you can provide us redundancy when we lose a tower.
Yep.
And I said, yeah, that's the virtue of mesh networking. We have no single point of failure.
Seamless redundancy, no single point of failure.
Yeah, if you watch a movie from that truck or that pickup that is traveling through the mine with both connections happening, let's say it's a POC and you intended shut off the mesh node that is receiving the traffic and putting back to the master. If that node is gone, you're going to see the video flowing normally because now the LTE is up. If that node is close enough to the LTE tower, maybe that link is going to become more, more stable, less latency.
Yeah.
And then, okay, I have mesh, but now I'm preferring to pass through LTE. So,
General
and you
experience-
can see it.
General experience about latency on LTE.
Oh, look, it's about 30 milliseconds. The
Yeah.
reality is, being a layer 3 technology,
Minimum 30 milliseconds.
you're looking at 30 milliseconds.
Yeah, I have worked with 20 to 25, up to 200. On the areas that is black, there's nothing there. It goes up to 300, and then you see mesh doing like 5, 7, 5, 7, 200. You know,
In generally, the latency is not the problem. The variation of the latency for trivial applications like teleoperations or autonomous stuff, the latency variation is the biggest problem, and that you will face with cellular technologies always.
yeah.
So
And
jitter as well.
Yeah.
And that is a good point. So these customers particularly called us because they wanted to have more bandwidth available. But they went to the telco said, "Oh, this is what you have here," right? And now they want to deploy tele-remote machines, tele-remote drills. There is no bandwidth available.
And this is
For
it.
real-time application.
And that's it. So you put a node there, you grab a PTP, name the brand, right? Make that PTP reliable, and now you have the drill talking back to the office in milliseconds. Very low latency, right? And many machines on the same node.